Perfect. Thank you, Tabata.
Okay, thank you. Hello, everyone. I'm Tabata. I am from Brazil, but nowadays I'm a postdoc here at LSU. I am very close to the Livingston Observatory. Today I'm going to give an introduction about detector characterization. Then I will try to show you some of the main responsibilities of the detector characterization group. We go through gravitational wave detectors trained data in both time and frequency domains. Then I'll show you the main types of noise in the detector, how we try to find out their source, and the data quality products that we have from there. And in the end, I'll give you a summary of O4A. All right, so what are the main responsibilities of the detector characterization group? The detector characterization, or DETCHAR group, focuses on both instrumentation and data quality. They investigate the detectors to identify and mitigate noise sources and provide data quality information to support gravitational wave searches and the validation of the candidate events. Ideally, we'd like to detect only gravitational waves, right? But unfortunately, it does not happen. Different factors can affect the detectors and create noise. And by factors, I mean instrumental oscillations such as electrical noise or detector instabilities, and also environmental conditions such as high ground motion, people driving around the detectors, trains passing nearby, wind, snow, and different factors. And we have two main types of noise in our data that we usually analyze. The first one is when we talk about longer duration noise. They are there for a long period of time. And we usually refer to that as line. The second type of noise is what are we call glitches. They are short in time, they have short duration, and they can decrease the statistics because they increase the background in the gravitational wave search. They can also not only increase the background, they can also mimic gravitational wave signals and overlap with real signals, what occurred during the first binary neutron star merger detection. So as you can see here, we have a signal during the coalescence, the merger of the binary neutron stars, and in the end, there is a loud glitch. One of the roles of the DETCHAR group is try to eliminate this noise, not only eliminate, but also looking for the sources of them. I will go through more details of each one of these types of noise. However, before I would like to go to gravitational wave detector data. As you saw in the first talk from Jane, the detector has this configuration. Of course, they are much more complex, but the basic idea is that. And we have a calibration way that we can measure gravitational strain amplitude given by h of t, that is equal the difference between variations in the arms over the length of the arms. All right, we can measure that, but how does this data look like? I have here an example of a strain during a random day and we're doing 4 seconds. As you can see, there is basically a morphology over time. Sometimes we are also interested, well, all the time we are interested in knowing about what are the frequencies present in this data. And then what we do is, since we have the strain data, we can apply some Fourier transform to check, to decompose the sines and cosines and be able to know what are the frequencies present in that data. Another way to see that is to understand how persistent a frequency was in the data that we are analyzing. And then we can say how much energy that frequency has in the data. And for doing that, we calculate what we call PSD, or power spectral density, which gives us a density of power of each frequency being in that data. There is another way to do that. Instead of looking at the power, is looking at the amplitude, and we usually call this amplitude spectral density. It's important to highlight here that in this plot, I am analyzing a long time of data. And when we do that, or when we do that in a quiet time, we basically have what we call noise spectrum of the gravitational wave detector, which is limited by different noise sources, such as fundamental sources, limited by physics, such as quantum noise, seismic noise, thermal. Seismic is kind of not that fundamental, but we also have some technical noise, such as 60 hertz, for example. If you look at this spectrum here, you can see a peak in 60 hertz, which is caused by the AC power line in the United States, presenting LIGO observatories in this case. Here I'm basically showing some data from LIGO, but it's very similar to the other detectors. And all the plots that have no references, I created using GWPy. All right, so it means that we can have the noise spectrum of the detector. Since we have noise, it's important to note that lower this curve, better we are. By knowing that, we can go to a plot from O4A that chart paper, where there is a comparison between O3B and O4A ASDs. Let's take, for example, Livingston. In light blue, we can see the noise spectra here with this morphology, while in dark blue, we can see the spectra during O4A. In light blue is during O3. And then we can see that during O4A, we were much better, which is amazing. All right, once we have the noise in the detector, we can go back to the time domain and try to see the morphology of the signals in the time domain. Why? Because if we look at the data here, for example, we cannot, from string, we cannot state anything about frequencies, right? We can say maybe that there is a dominance of low frequency, but we cannot see a presence of a signal. For example, here I have the signal during the first gravitational wave detection in Hanford, and here I have a transient noise signal. And if you compare these two plots, we are not able to say where is the signal, if it is whether it's a glitch, if it is a gravitational wave signal. So what we usually do is we have our time series, our raw data, the string data, and then we apply the Fourier transform, and the result we divide by the ASD, which is the noise spectrum of the detector. In this way, we are doing what we call whitening the data, and then we are removing the shape of the noise of the data. And basically, we are normalizing, and we are able to see all frequencies equally with the same weight. Here I have examples of the same data, whitened. If you look at here, for example, in Livingston, we see oscillations around 0 and a really high spike, strong spike here. It happens because this is a loud glitch, a very loud glitch, and loud I mean very strong. And we are able to see this spike because of that. But if you look at Hanford data, we are not able to say where is the gravitational wave signal, right? And because of that, there's some other process or filterings that we can apply to help us to look at the data in the time domain. For example, we have high pass, which means that we want to look at frequencies only above a threshold. We also have low pass that we want to look at frequencies only below a threshold, and we have band pass that we want to look at frequencies between two thresholds. Here I have what we get when I apply a band pass between 20 and 250 hertz. And now the morphology of the gravitational wave signal is much clearer. We can see the amplitude increasing over time here. All right, now that we have an idea about data, let's talk about gravitational wave detector noise. As I said, we have persistent or slowly time varying artifacts called lines in our data. When I showed you the ASD, we saw some lines, including 60 hertz, that they are there all the time. You cannot escape from them. And sometimes we also have those that slowly vary, which what I mean with that. Sometimes a line appears during 1 week, 1 month, and disappear and come back again. Sometimes we have no idea why. Sometimes we try to associate modifications in the interferometer to try to understand why the line disappeared or appeared again. Usually we can split the lines in three types. There is the narrow line, this one here, which has a really very well defined frequency. We also have broad lines. As you can see, they are broader in frequency. And we have combs that looks like combs. We have repetitions at certain frequency. For example, we have a comb that repeats every 1 hertz in the day. That share usually get information from different tools, such as FSCAN and Stockmon. I will not go to details of the tools, but there are some references at the end of these slides that you can basically access and read and ask questions if you're interested. And as I said, this kind of source impact especially continuous wave sources. So it's very important to understand them and eliminate or mitigate their impacts. All right, the second type, short duration artifacts or glitches. As I mentioned, these glitches increase the background noise, may affect the parameter estimation, and can mimic a real gravitational wave signals. The chart uses a tool called Omicron, which searches for excess power in the data. When you have your data and there is an excess power in the data, Omicron finds it and then assign some information such as time, frequency, and signal to noise ratio. So every time there is a glitch in the data, Omicron finds it and characterizes it by assigning these parameters. I have here one example that we usually call glitchgrams, where each data point represents a glitch. And as you can see, there are many of them. In the vertical axis, you can see the frequency, and this is during a whole day. So we have time in hours in the x-axis, and the colors represents the SNR. We have a lot of glitches with low SNR, especially here at higher frequencies, and there are also some glitches with high SNR, randomly distributed. So you have an idea. Here we have a plot doing O4A and O2B of the glitch rate per hour. The glitch rate per hour, sorry. In Hanford, for example, we had that when considering glitches with SNR above 6.5, we had around 77 glitches per hour. And then we increased this threshold to considering glitches with SNR larger than 10, we start to have around 6 glitches per hour. In Livingston, during O4A, we had around 53 glitches per hour, considering low SNR glitches, and around 31 glitches per hour, considering glitches with SNR larger than. And how are glitches usually studied? Well, we saw that we can have information about data in the time domain and also in the frequency domain, right? What if we could have both information at the same time? We can do that by using spectrograms. Spectrograms are basically a representation of the data in the time and frequency domain. I have here an example of this glitch, this transient noise, represented by spectrograms, where you can see now how the frequency changes according to the time. So for example, in the beginning, we have that this glitch reach only low frequencies, but in the middle of the glitch, we have higher frequencies. So it's very important to read this kind of information because we can associate and create some um, features related to the glitch. For example, when we look at glitches at this spectrogram way, we can see a morphology of the glitch. And this is very important because it's the way we usually study them. Usually, spectrograms can be created by applying Fourier transform. However, to analyze glitches, we create spectrograms based on the Q-transform. Q-transform is a modification of the Fourier transform, where there is a window, almost a Gaussian window, which multiplies the data. And this window depends on a quality factor, or Q, which is proportional to the frequency of the window over the bandwidth of the window. What does that mean? If you look at here, this is a representation of the time frequency domain. And we have what we call tile, this region here, with a duration delta t and a bandwidth delta f. So we have this region, a lot of regions. When we created a spectrogram from Fourier transform, this delta t and delta f are always the same. They are constant all the time. When we apply the Q-transform, we can create a trade-off between either have good resolution time or good resolution frequency. Because these tiles here have the same area, but they don't need to have the same delta t and delta f. In other words, we can basically create spectrograms for different Qs, which will bring us more resolution in frequency or more resolution in time. For example, I have here, for example, consider that Q is increasing for a semi-frequency, high Q implies that delta, the bandwidth delta F is lower, which means the resolution in frequency is better. If we have a low Q, it means for a constant frequency, it means that the bandwidth is larger and the resolution frequency worse, which implies good resolution in time. I know this is a bit complicated to understand, but the main idea is high Q, better resolution frequency, and low Q, better resolution time. I will give you here an example to become clear. I have a morphology of a glitch, right? Here is one of them. In this case here, you can see repetitions of these spots, right? And we are very interested about these repetitions because we want to know the frequency of the repetitions. And sometimes they bring information about the sources. So it's very important to have this information. When I apply the Q-transform using a Q value, you can see a good resolution time. So we can see very well this behavior. If we increase the Q value, we start to lose information in time. As you can see here, the spaces are not that clear anymore. And then if we increase and increase, we are basically lose all the information time and only have good information frequency. All right. And why? Why do you want to have different Qs? As I said, it's important because the morphology, the way that we look at the glitches in the spectrograms can bring some information about sources. For example, we have here this fast scattering, the name of the glitch. And we see that, as I showed before, there is this space among these spots, which is very important. And this is related to some ground motion, and the repetitions can bring information about the frequency of the ground motion. On the other hand, we have here another kind of glitch. And in this case, we are not interested in knowing about repetitions in time, but I'm interested in knowing about harmonics of the signal. And in this case, it's much better have It's much better to have better resolution in frequency. All right, so we can adapt the queue according to what is better for our analysis. Usually, what people realize that some glitches, some noise transients appear many times in the detector. And then they realize that looking at the morphology of the glitches, we could start to create some classes for glitches. And this is what we do. For some glitches, we have names to classify that glitch. Because since we have many of them, it is important to create a group to identification later and try to looking for their sources, for example. I have some examples here. The first one is Tonte, the second is Blip, this one is whistle, fast scattering, scatter light, and extremely loud or loud glitch. It was one of the examples I showed before. There is a tool called the Gravity Spy, which classifies these glitches and assigns them names according. The names are given according to their morphology or sometimes according to their sources. We don't necessarily know the source of the glitch, but sometimes we do, and then we can classify them accordingly. There is a Zooniverse platform. It's public. It's open to everybody interested in helping classifying glitches and learning about them. Right, but why we have classes of glitches? I mentioned that before, but I would like to make this clear now. When we have classes, we basically uh, can select a group, select the class, and try to track the behavior of this class over time, or try to study some statistics information from that class, which means that we can try to looking for patterns in the data to try to bring information from their source. To bring information from their source, we usually use what we call auxiliary channels that record information from different sensors around the detector. Sensors such as seismometers, accelerometers, thermometers, and a lot of them, which are there just measuring everything is happening around the detector and give us data and information about it. How does it work? I have here an example. Let's suppose this is our strain data, right? We have some transient signals, four transient signals in our data. And then if we look at some auxiliary channels, microphone, for example, we see that two transient signals are related to microphone uh, signals at the same time. And there is another signal here related to strong wind. So in this case, we can say, whoa, let's be careful because those signals in the gravitational wave channel, as we usually call, where there is the strain amplitude, uh, the signals there cannot be gravitational waves. They may be coming from environmental conditions. Sometimes we have an earthquake, and then we can say, oh, that signal is due to earthquake, not is not a gravitational waves. So it's important to use the information about auxiliary channels to help us provide quality information about data. I have here an example, of a real case, and where you can see the vertical bars represents the glitch per minute, and the blue line represents the velocity of the ground motion. There is a seismometer very close to the beam splitter, where it's measuring ground motion around it. And in this case, we are plotting the motion in a frequency between 10 to 30 hertz. And as we can see, the increase of glitches match clearly with variations in the seismometers. So in this case, we have some indication of the source of what is causing those glitches in the detector. There are some other tools as well that share usually to help in the analysis of looking for sources and auxiliary chains information. I have some examples here, which are HVIDO and IDQ. I also give some references for them. We usually have a lot of auxiliary channels, thousands of auxiliary channels, and we need to be sure that we can use that auxiliary channel to say if there is a noise in the detector. For be sure to do that, the Detector group, we apply what we call hardware injections, which is basically create a signal detector and see what are the auxiliary channels responding to that signal. And in this way, we can create a list of safe and unsafe channels. The safe basically means that we can use that information to have indications about the noise. All right, sometimes we can find the source of these glitches. Sometimes we can eliminate them. Other times we can just mitigate their effects. And sometimes we have no idea what is happening. And to help with that, what that share group usually does is creating some flags, some data quality problems. Basically, the group analyzes potential issues in the data, defining segments to be videoed. These videos are categorized according to the severity and understanding of the underlying problem. For example, have category 1 or CAT 1, which indicates periods with technical problems or critical issues involving key detector components not in operating their nominal configuration. In other words, we should not use the data during this time. CAT 2 mark times with no noise couplings to the strength channel. And for example, sometimes we know that there are many glitches caused by hardware motion. So we can categorize that segments, that times that are associated with ground motion. And CAC3, that we know that are some statistical correlations between the strain and auxiliary channels, but we are not sure how this coupling is working. And then sometimes use information from HVIDO, for example, we know there is a correlation, but we have no idea why sometimes. And then we created this category. And yeah, that's it. I think I'd like to end with offer a summary. That chart usually has access to summary pages, which give us information about detectors in real time. And then we can try to create some hypotheses and see what happened in the detector during the observing ones. There is also a public summary page you can access here. And then from there, you can get information about the gravitational wave observatory status. You can get, for example, a summary like that from O4A, which gives BNS range for each detector, gives observing segments for each detector, how much time, what was the percentage of both detectors were working together. We also can access the GraceDB, which gives us alerts about gravitational waves, right? And doing O4A, for example, we had 92 alerts from where 11 were retracted. And in O4B, we had 105 significant detection candidates. And that's it. I think the main idea of the Detector group is try to help with data quality and, of course, with gravitational wave searches. And that's it. Thank you so much for your attention. I'm glad to help and happy to answer any questions.
Perfect. Thank you, Tabata. That was excellent.